Hi everyone, this is lecture 3 of the electronics course. Let's start with a quick recap of what we did last time. So we were interested in looking at transient circuits in which the output depends on time. So we started off by looking at a CR circuit, and we studied it in both charging and discharging modes. And then I said you can do the same thing with an LR circuit as well. And I hope you had time to try and do the same calculation at home one more time. Then we looked at the response of these circuits to a square wave. And then finally we started looking at AC inputs. When we were doing AC inputs, we realized that if you have an AC circuit with a resistor in it, then the voltage and the current are in phase. But if you have an inductor, then the current lags behind the voltage, and if you have a capacitor, then the current leads the voltage, and both of these are by a phase of 90 degrees. We defined inductive reactance and capacitive reactance, which are basically like the internal resistance of these components. What else did we do? We looked at the power dissipation, and we saw that resistors are dissipative elements, but inductors and capacitors are non-dissipative. So this is what we discussed last time, and today we'll continue with some more of this discussion on AC theory. All right. So the first thing that I want to introduce today is a few concepts such as RMS voltage, peak-to-peak voltage, and peak voltage. So let's start with a simple diagram. So this is what an AC voltage looks like. Let's say it's a sine wave. So let's call this V is V0 sine omega t, where V0 of course is the amplitude of this wave. So this is plus V0, this is minus V0. So the first thing that we define is the peak voltage, and this is V0. This is the maximum possible value that the voltage can take. The next thing that we will define is peak to peak voltage, which, as the name suggests, is not from 0 to the top, but rather from the top to the bottom. And this will, as you may have guessed, so we call this V P to P. This is going to be twice of V0. And the third thing that I want to define over here is what is called the RMS voltage. Now RMS voltage, so this stands for root mean square. So this is a way of defining an average or a mean over the sine wave. If you just directly take a mean, you're going to get 0, obviously, because the sine wave is positive in some parts, negative in some parts in equal measure. So we define what is called the RMS voltage to give us some indication of what the magnitude of this voltage is. And the way you define it is given in the name itself, root mean square. So you want to first take the square of the voltage, then you want to take the mean, and then the root. So this is the RMS voltage. Let's calculate this for this particular sine wave that we have over here. So this is square root of the average value of V0 square sine square omega t. Average of sine square, as we have discussed before, is half. So this is V0 divided by root 2. Numerically, it comes out to be around 0.707 V0. So around 71% of the peak value. So if I were to draw it, it would be somewhere over here at 70% of V0. So that is the RMS voltage. Oh, I see, you cannot see that very clearly. So this is the RMS voltage. In general, for any kind of sinusoidal wave, you can define these quantities: the peak to peak, and the RMS. Okay. So now the next topic we'll discuss over here is the use of complex numbers in analyzing AC circuits. So first, just let's quickly review complex numbers. So in general, a complex number is defined as x plus iy, where I is square root of -1. So x is called the real part of the complex number, and y is called the imaginary part of the real number. And you can plot a complex number on the complex plane. So this is the real component, this is the imaginary component, and x plus iy would be somewhere over here, where this is the x component, this is the y component. Now, of course, you can also represent a complex number in polar form. So we define the distance of this real number from the origin as r, and the angle that it makes with the x-axis as theta. And then you can see that x is going to be r cosine theta, y is going to be r sine theta, which means that we can write z as r cosine theta plus I r sine theta. And then you can use Euler's formula to write this as r e to the power I theta. So you can express complex numbers either in this form, which is the Cartesian form, or you can write it in this polar or trigonometric form, or in the exponential form. Now, why exactly are we using complex numbers? Because the reason we are doing it is because you can write it in this polar form, which involves sines and cosines, but also in this exponential form. And that is going to make some of our calculations easier. And just to give you some extra information, this is true not only in electronics, but anywhere where you're dealing with electromagnetic signals. So in analysis of electrical circuits in general, in electromagnetism, in optics, wherever you have sine waves, it can be quite convenient to use complex numbers instead of real numbers to do mathematical analyses. So in our context over here, since we are often dealing with voltages which look like this, now what I can do is I can write it as the imaginary part of the complex number right? And similarly, if I have a current which looks like this, why have I written this plus 5 over here? Because this depends on whether the current is passing through a resistor, an inductor, or a capacitor. Accordingly, it will either be in phase with E, in which case phi will be 0, or it will lead or lag, in which case phi will be plus 90 degrees or minus 90 degrees. So I just kept this phi over here to be general. So if this is my current, then I can write this in complex notation as the imaginary part of e to the power I omega t plus phi. Or actually I can even split this further. So we are going to use this extensively. We will always write our voltages and currents in terms of complex numbers, and we'll see what advantage that gives us. So let's now look at a physical system. Let's look at an LCR series circuit. So far we've looked at LR circuits, we've looked at CR circuits. Now we are putting all three together, LCR, in a series along with an AC voltage. So a circuit now looks something like this. So resistor, capacitor, inductor. And let's call this AC source E. What is the equation that describes this circuit? We'll use Kirchhoff's voltage law again. So E is going to be, for the resistor we have IR, for the capacitor we have Q divided by C, for the inductor we have L di by dt. Now what we'll do over here is, we don't want to deal with charges, so let's just take a time derivative of this entire equation. dq by dt is just the current. Now we have this entire equation in terms of voltages and currents. Let's substitute them with complex numbers as we said we would do. So I'm going to replace E with E0 e to the power I omega t, and I am going to replace with I0 e to the I omega t e to the I phi. Of course, right now I'm calling them complex, but in the end, once I finish my calculation, I should make sure that I take the corresponding either real parts or imaginary parts. Okay, let me go back one step. So whether I write, I'm free to write my voltages and currents either as sine waves or as cosine waves, because they're just a shift in 90 degrees. So I can either choose to do my analysis with the real parts or the imaginary parts. Real parts will give me cosine, imaginary parts will give me sine. So over here, because consistently we've been doing sine omega t waves, we are talking about taking the imaginary part. Now voltages and currents are always, in principle, they're always real numbers, because these are things that you actually measure in the lab, in any experiment. So finally, in the end, all our answers have to be real. What we're doing mathematically is just a convenient trick in order to simplify our calculations. So remember that point. So here we are replacing the voltage and the current with these complex numbers. And now we'll plug them into our differential equation. So when we do that, dE by dt becomes I omega E0 phi is constant in time. Oh, you can't read this. Let me just write this part again. Now I'm going to do a couple of things over here. Let's first get rid of all of these e to the power I omega t because they appear everywhere. Great. Now the next thing I'm going to do is I'm going to absorb this e to the power I phi inside the I0. So if you look over here on the left side, I'm going to write this as I0 prime e to the I omega t. So I0 prime is I0 e to the power I phi. It's not time dependent, so it doesn't change any of the dynamics. So then I can rewrite this equation as I omega E0 omega A0 prime R plus I0 prime over C plus I square omega square L I0 prime. And now I will define E0 divided by I0 prime, which is right. And this is a very important equation. Let's rewrite it. Or I can write this as and this is because I square is minus 1. So 1 over I is just minus I. Now on the left hand side we have E0 divided by I0 prime. So this is like a resistance. And this resistance has a special name. This is called impedance. Impedance is the overall resistance of the circuit, taking into account the effect of the resistance, the inductance, and the capacitance. And as you can see on the right hand side, this is I. Omega L is the inductive reactance. 1 over omega C is the capacitive reactance. So Z takes into account all these three resistances. Of course, Z is a complex number because it is E0 divided by I0 prime, and I0 prime is complex. So what is physically relevant is the magnitude of this number Z, and this is given by R square plus XL minus XC the whole square. So in general, if you have a circuit which contains resistors, inductors and capacitors, then this is how you calculate the overall resistance of this circuit. Okay, now